Alright, so this set of notes that I'm recording today is the rest of these 4-3 notes. The factor by grouping portion of this lesson has already been posted on YouTube, so this would be the first half of that lesson. The reason these are recorded in separate pieces is because our quiz today was only over the second half, so I did not want to confuse anyone and have too much information to review before this date. So the first half of this section is discussing solving quadratic functions by factoring, and that is all based on this idea of the zero product property. Now this is also known as the zero factor theorem in other books. What it boils down to is that if I have two or more real numbers, a and b, and I multiply them together to equal 0, the only way that that can occur is if either a equals 0 or b equals 0. This ends up being an extremely useful tool to us as we solve quadratic and other equations. So for instance, here on letter A, we have two sets of parentheses that are being multiplied together to equal 0. This means that one of those two sets of parentheses has to equal 0. So when we use the zero product property, what we're doing is taking each of those factors, each of these factors, and setting them equal to 0. So our solutions come from either x minus 2 equals 0 or 4x minus 1 equals 0. We would then go and solve each of these two equations the way we always have in algebra class. So we would add 2 to each side of the first equation, which would give us our first solution of x equals 2. The second equation is a two-step equation. First we would add 1 to each side. Oops, 1, not 4. Let's fix that real quick. We would add 1 to each side, which would give us 4x equals 1. And then we would divide by 4, which would give us x equals 1/4. So our two solutions to this equation would be x equals 2 and x equals 1/4. We'll do a couple more examples here so that we can see this a few more times. So on letter B, we have two factors, 7x times the quantity x minus 3 equals 0. This means that either 7x equals 0 or x minus 3 equals 0. So we would start by solving the first equation by dividing each side by 7, which would give us the solution x equals 0, or on the other equation we would add 3 to each side of the equation, which would give us the solution x equals 3. So the solutions to that equation would be x equals 0 or x equals 3. Same thing down here, 2d plus 6 equals 0, or 3d minus 15 equals 0. So we're going to solve each of those equations. They're each a two-step equation. So on the first equation, I would subtract 6 from each side, which would give me 2d equals negative 6. And then I would divide each side by 2, which would give me d equals negative 3 for my first solution. Second solution, I would add 15 to each side of the equation, which would give me 3d equals 15. And then I would divide by 3, and that would give me that d equals 5. So my solutions to that equation are d equals negative 3 or d equals 5. Same thing on letter D. We would set 3n equal to 0, or we would set n plus 2 equal to 0. Each of those is a one-step equation, so the first one we would divide by 3. 0 divided by 3 is still 0, so our first solution is 0. And on the other one, we're going to subtract 2 from each side, which would give us n equals negative 2 for our second solution. Now, there are a number of different types of factoring, and the first type of factoring requires us to remember a skill that we learned in junior high. That is how to find the greatest common factor, or GCF, of a pair of monomials, or a group of monomials, or a group of numbers. So we'll go over this skill as if we've never learned it before, but then when we get into the actual factoring problems, it will be assumed that we know how to do this, because this is, as I said, a junior high skill. If you need more practice on this, that's the whole point of us having IXL, is so you can go back and practice things that you're not very good at. So what we're going to be doing, essentially, is breaking these down into their prime factors. A prime number is, of course, a number that is only divisible by itself and 1. Those numbers would include 2, 3, 5, 7, etc. Numbers like 4 and 8 are not broken down far enough because they're divisible by more than just themselves and 1. So for instance, we're going to take each of these numbers and write them as a product of their prime factors, a prime factorization. So 16 is 2 times 2 times 2 times 2. That is the prime factorization of 16. 40 is 2 times 2 times 2 times 5. Finally, 64 is 2 times 2 times 2 times 2 times 2 times 2. 6 sets of 2. Now when we want the greatest common factor, it's really the same process to find this or the least common multiple except for the final step. So what we need to do is go in here and we need to figure out what they have in common. So if you notice, each of these 3 lists contains a total of 3 2's. From that point forward, there aren't any more 2's we can take because 40 is out of 2's. We can't use this 5 either because neither 16 or 64 is divisible by 5. So our GCF for these 3 numbers would be the sum, or the product of what I circled here. So we have a 2, another 2, and a final 2. So the GCF would be 2 times 2 times 2, or 8. So we're going to do the same thing for these other numbers here. 9 is 3 times 3. 18 is 2 times 3 times 3. And 30 is 2 times 3 times 5. So this one's actually a little bit easier because the only thing that those 3 numbers have in common is 3. We can't take a 2 because 9 is not divisible by 2. There's no 2 in the 9 list. We can't take another 3 because 30 only has one 3, so they can't take a second one. And we can't use 5 because neither 9 or 18 is divisible by 5. So our GCF would simply be 3. So then we move into expressions that contain variables. And we do this, I believe, in 7th grade. Might be 8th grade, but either way, it's not a big deal. When we go in here, we think to ourselves, we're going to pick, up here, it says right up here, the greatest common factor of variables with exponents is the smallest exponent on each variable. So in letter C, we have 2 variables. We have x, and we have y. So we're going to look at each of those variables, which do exist in both expressions, and we're going to pick out the smaller exponent. So of our 2 options with x, we have x to the 5th and x to the 9th. The smaller exponent would be x to the 5th. So that's the one we would select. For the y, I have a y to the 3rd and a y to the 1st. So the y to the 1st would be the smaller exponent. This means our GCF would be x to the 5th, y to the 1st, or x to the 5th y. So let's do another one of those. On letter D, we have x to the 12th and x to the 3rd. The smaller would be x to the 3rd. For y, we have y squared and y to the 7th. So the smaller of those 2 would be y squared. This makes the GCF of these 2 monomial terms x to the third y squared. Now, when we combine those two skills, the numbers and the variables, we simply combine those two approaches. Okay? So, for 7, 9, x to the ninth, y to the fifth, it's actually a really easy one to factor because 7 is a prime number. So we have 7, we have an x to the ninth, and we have a y to the fifth. For 28, x to the 12th y, 28 is 2 times 2 times 7. Then we have an x to the 12th and a y to the first. So when we go in to select our greatest common factor, the first thing we do is look for common factors for the numbers. The only common factor is a 7. Then we select the smaller of the two x values, which would be x to the ninth, and the smaller of the two y values, which would be y to the first. So our greatest common factor here on letter E would be 7, x to the ninth, y to the first. Let's do one that's a little bit harder. It's not a lot harder, it's just a little bit harder. 15, x to the eighth is 3 times 5 times x to the eighth. And 25xy is 5 times 5 times x to the first times y to the first. So when we go in looking for common factors, we find a 5. That's all we can take for numbers. For x's, we would choose the x to the first because that's the smaller exponent. And that raises a new point because now if we go to look at y would not be included in the greatest common factor because there's only a y in one of our two lists. There is no y on 15x to the eighth. So y cannot be part of the greatest common factor. So the greatest common factor would be 5x to the first. Okay, moving into factoring the greatest common factor out of each polynomial. What we're going to be doing is looking for the greatest common factor of our terms and then factoring that out of the polynomial. Now when we factor a greatest common factor out, what we're really doing is the opposite of distribution. So we're going to be dividing. So if we look at the first one, 27x squared, 27 is divisible by 9, as is 18. So our greatest common factor for 27x squared and 18x would be 9x. So we're going to pull that greatest common factor out. And what happens when we pull out the greatest common factor is we have to divide each term by the greatest common factor. Now once we get good at this, we don't need to show this work. But until we understand what we're doing, it can't hurt to write this out. So we would divide each of these terms. 27x squared divided by 9x would be 3x, and 18x divided by 9 would be 2. This is the factored form of this binomial. I factored out the 9x. Let's do another one. On B, 14c squared and 2c have a greatest common factor of 2c. So we're going to divide each of those two terms by 2c. When we do that, we're left with 2c times the quantity, because we just bring this straight down. 14 divided by 2 is 7. C squared divided by c is c, so 7c. And then 2c divided by 2c is 1. It is very important that we don't just drop that term thinking that it goes away, because it doesn't. 2c divided by 2c is like 3 divided by 3. It's 1. So we can't just drop it. Now we can extend that from binomials out to trinomials very easily. If we look at letter C, all three of these terms are divisible by a 2. They all have at least one x, and they all have at least one y. So the greatest common factor would be 2xy. Again, what we're going to be doing there is dividing each term by 2xy. So each term in this expression is going to be divided by 2xy. So that will give us 2xy times the quantity. This here divides to be negative 2x, because the y's would cancel each other out, minus 8 divided by 2 is 4, the x's cancel, y squared minus y is y, so 4y, plus 1, because these are the same, so they would cancel and leave a 1. Final example. All three of these are divisible by 2mn. So that is our common factor. We're going to divide each term by 2m to the first, n to the first. And then reduce. So that would be 2mn times 2mn plus m, because it would be 1m, but we don't have to write the 1, minus 5n. So now we're going to put those two things together, factoring the greatest common factor and solving using the zero product property. This simply means that the directions have changed from factor to solve. That tells us that our final answers should be x equals a number or x equals a number. Now we know there's only going to be 2 because of the degree, but we haven't gotten that far yet. So, on letter E, first things first, the expression has to equal 0 in order to be solved. So we're good on that situation here. But later on, look down here, see it? We're going to have to do something before we start factoring. Okay, so 5x squared plus 10x can be factored. It has a greatest common factor of 5x. So we factor out 5x, which leaves x plus 2. Now this expression looks like the ones we solved earlier. So we're going to break that up into two separate equations. 5x equals 0 or x plus 2 equals 0 using the zero product property. Our final step then would be to solve each of these expressions, each of these equations. The first one, we would divide each side by 5. 0 divided by 5 is still 0. So the first solution is x equals 0. Or the other one, it's a one-step equation as well, but to solve it we need to subtract 2. So our second answer would be x equals negative 2. On letter F, these two terms are each divisible by 8 and each have at least one x. So the greatest common factor would be 8x. When we factor that out, remember we are dividing each term by 8x. So 8x squared divided by 8x is x. 40x divided by 8x is 5x. I'm sorry, just 5, not 5x. Good call. Alright, so that equals 0. We're then going to apply the zero product property, which tells us that 8x equals 0 or x minus 5 equals 0. And again, we're going to solve. So the first equation we divide by 8. 0 divided by 8 is still 0. Second equation, we're going to add 5 to each side, which would give us x equals 5. So our solutions would be x equals 0 or x equals 5. So that brings us to letter G. Now if you notice, the difference between E and F and G and H is that G and H are not already set equal to 0. So your first step is to move everything to one side of the equation. Now it doesn't technically matter which way you move it, but I would always move everything to whatever side will make the x squared term positive, the lead term. This is the highest degree term. So we would subtract 4x from each side. Keep in mind that these can't actually be combined. That would turn this into x squared minus 4x equals 0. Now it's exactly like the ones we did up above. we're going to factor out the greatest common factor, which would be x, and leave us with x minus 4. Then we apply the zero product property. So we would have x equals 0 or x minus 4 equals 0. X equals 0 is already solved, so we just circle that one. That's one of our solutions. And on the other one, we add 4 to each side, which gives us x equals 4. So our solutions would be x equals 0 or x equals 4. Same thing here on letter H. We need to move the 12x to the left. These are not like terms, so they don't actually get added. We just move the 12x to the left side where it becomes positive 12x. And that would now equal 0. So we're going to factor out the greatest common factor here, which would be 3x, and would leave 3x plus 4 on the inside. Break that into two separate equations using the zero product property. And those two equations are going to give us our solutions. Either 3x is equal to 0, which we solve by dividing 3 and getting x equals 0, or the second equation here, we're going to have to subtract 4 from each side, which would give us 3x equals negative 4. And then we would need to divide by 3, which would give us the second solution as being x equals negative 4/3. So those are our two solutions for that final equation there. Okay, so here's a word problem that deals with greatest common factor. It says, Penny is a fox terrier who competes with her trainer in the agility course. Within the course, Penny must leap over a hurdle. Her jump can be modeled by the equation h equals negative 16t plus 20t, where h is the height of the leap in inches at t seconds. So part A says let h equal 0 and asks us to write the equation in factored form. So we're going to take that 0 and plug it in for h. That would be 0 equals negative 16t squared plus 20t. Now it says write it in factored form, so that means you need to factor the right side of that equation. Since there are only two terms there, we check for a greatest common factor. The greatest common factor would be 4t. So that would be 0 equals 4t times negative 4t plus 5. Now you could also factor out negative 4t, which would make this positive 4t minus 5. Either way, you will end up with the factored form. So there are really two different factored forms. Okay, either one of these would be acceptable. You could also say 0 equals negative 4t times 4t minus 5. Either one of these would be an acceptable factored form. Part B says solve the equation. So we're going to take our equation, I'll use the first one, and we need to apply the zero factor theorem. 4t equals 0 or negative 4t plus 5 equals 0. And we solve them just like we did on the previous page. So on the first problem, we would divide each side by 4, which would give us t equals 0. And on the second equation, we would subtract 5 from each side, which would give me negative 4t equals negative 5. And then I would divide by negative 4. Now, two negatives mean that this t would equal positive 5/4. And I don't know about you, but I don't often say that I traveled for 5/4 seconds. So perhaps we should change this particular number into a decimal because it represents seconds, and that would make more sense in the context of the situation, which is where we're getting ready to go here. Now, this is a word problem. They asked us a question, so we should answer that question with words. What do these solutions represent in the context of the situation? Well, the first solution, t equals 0, the dog has not jumped yet. So, Penny is still on the ground. The ground, of course, being h equals 0. What about the other one at 1.25 seconds? Well, at that point, the dog has already jumped, meaning that she is landing. Okay, so she jumps and lands. Those would be the 2 points in time where she's on the ground. Moving on. I would assume that this section might be one we look into. It is one of the two things covered in one of our IXL topics this week, and that is the difference of two perfect squares. We've discussed previously how very, very important it is that we know our perfect squares. Those are the numbers that have exact square roots, such as 1, 4, 9, 16, 25, 36, 49, etc. And that's because of this kind of factoring. If A and B are natural numbers being your numbers that you count with, 1, 2, 3, 4, 5, 6, 7, 8, 9, or if they are variable expressions with even exponents, so the exponents are 2, 4, 6, 8, 10, 12, 14, etc., then what we can say is a squared minus b squared factors into a plus b times a minus b. That is, if this first term is a perfect square and the second term is a perfect square, it will factor into the square root of the first term plus or minus the square root of the second term. So let's look at some examples. Okay? X squared is a perfect square because the square root of x squared is x. 9 is a perfect square because the square root of 9 is an exact value 3. Notice it is subtraction. That makes it a difference of two perfect squares. That means that this expression will factor into the square root of the first term, which was x, plus or minus the square root of the second term, which was 3. Same thing for this next problem. 4x squared is a perfect square because 4x squared has a square root of 2x. Notice the root is gone. 25 is a perfect square because the square root of 25 is 5. We have a subtraction symbol. That makes it a difference of two perfect squares. And that means it factors into the square root of the first term, which is 2x, plus or minus the square root of the second term, which is 5. So let's look at some examples of that. Before we do that, it is very important to note that in all types of factoring, before you do one of these algorithms, before you factor difference of two squares, you are always, repeat, always supposed to start exactly the same way, and that is by factoring out the greatest common factor. Now remember, you can only do that if there is one other than 1, because everything is divisible by 1. So we'll start by factoring out the greatest common factor, and then we will factor difference of two squares. Again, that's x squared minus y squared is x plus y, x minus y. Notice how I changed the variables, because you can make the variables whatever you want them to be. So 4x squared minus 16. You might think, oh, those are perfect squares. I should go straight to step 2. No. They are divisible by 4. So your first step has got to be to factor out the 4. The reason for that is if you do not, you will not be finished factoring. Now once we factor out the 4, the binomial that remains, we check to see if this is still a difference of 2 squares, which it is. X squared has a square root of x, and 4 has a square root of 2. So we do have a difference, see the subtraction symbol? Difference of 2 perfect squares. Now that raises a question, what about this 4? Well, that 4 is already part of the answer, so it's just going to sit out in front. Then we're going to factor this binomial. So the square root of x squared is x. That's the first term in each binomial answer. One's a plus, one's a minus. Square root of 4 is 2. So our final factored form would be 4 times x plus 2 times x minus 2. Let's do another one. Here on letter B, the GCF is 2x. That would leave 4x squared minus 1. 2x is done. We can't factor that any further. But 4x squared minus 1 is a difference of 2 perfect squares. So it would factor again. Again, it's a difference, see the subtraction symbol, of 2 perfect squares. 4x squared has a square root of 2x. 1 has a square root of 1. So we would take the square root of 4x squared, which is 2x, and that would be the first term in each of our binomials. One would be a plus, the other would be a minus, and the square root of 1 is 1. Let's do a few more examples just to make sure. Okay, letter A. First problem here is a difference of 2 perfect squares. So that one's an easy one. We're just going to factor those. The square root of x squared is x, plus or minus, the square root of 81 is 9. Completed. Letter B shows something that comes up occasionally in Algebra 2, and that is an exponent greater than 2. So first we check for greatest common factor. There is not one. So we go ahead and we factor difference of 2 perfect squares. Again, 16 is a perfect square, 81 is a perfect square, x to the 4th is even. So this is a difference, subtraction, of 2 perfect squares. The first term in each of our parentheses is going to be the square root of 16x to the 4th, which would be 4x squared. 1 is a plus, 1 is a minus. And the second term will be the square root of 81, which is 9. Now you might be thinking, great, I understand this, makes perfect sense, I must be done. But this problem is not fully factored yet. The first binomial is fully factored. This cannot factor again, so this is now a prime factor. However, this parenthesis is still a difference of 2 perfect squares. 4x squared has a square root, 9 has a square root, and they're being subtracted. That's why this one doesn't work, because it's not being subtracted. So 4x squared minus 9, or plus 9, is one of our factors. But 4x squared minus 9 will factor again. The square root of 4x squared is 2x, so the first term in each of our binomials is 2x. One's a plus, one's a minus, and the square root of 9 is 3. That is now fully factored. On letter C, these don't look like perfect squares, but they have a greatest common factor. Both of those terms are divisible by 3x. When I factor out 3x, I'm left with 4x to the 4th minus 9y to the 8th. Now these should look like perfect squares. So again, the 3x is part of the answer, and we can't just forget about it and let it sit out there. It's got to sit out there and be part of the answer. You can't just forget about it and finish, because if you do, you won't have an equivalent expression. Okay? So, the square root of 4x to the 4th is 2x squared. The square root of 9y to the 4th, oh, one's a plus, one's a minus. The square root of 9y to the 8th would be 3y to the 4th. That is fully factored because even though the exponents are even, 2 is not a perfect square, nor is 3. All right, on letter D, no common factors. 64 is made up of a whole bunch of 2's. 625 is made up of a whole bunch of 5's. They don't have anything in common. They are, however, both perfect squares. So we start by factoring the difference of two perfect squares. The square root of 64x to the second is 8x. So we have an 8x for the first term in each set of parentheses. One's a plus, one's a minus. And the square root of 625 is 25. Hopefully, you knew that already because you've been studying your perfect squares that I asked you to memorize up to 25 squared. That's done because 8 is not a perfect square. So even though it's subtraction, and even though 25 is a perfect square, 8 is not. So this is not a difference of two perfect squares. And this is a sum, so it's not even a difference, let alone a difference of two perfect squares. Okay, so here's a couple more. We're just going to burn through these really fast because they're the same thing we just did on the previous page. First one does not have a GCF, so we factor the difference of two perfect squares. Again, the square root of x squared is x. One's a plus, one's a minus. The square root of 400 is 20. And that problem is complete. These are the ones that we did in class on our own and then got checked. On number 2, we're going to factor out the 7x, that is the greatest common factor, which would leave x to the 4th minus 4. This is a difference of two perfect squares, so it will factor again. The 7x remains as part of our factored answer. The square root of x to the 4th is x to the 2nd. One is a plus, one is a minus, and the square root of 4 is 2. This and this are both finished. This is a sum, so it doesn't factor again. And even though this is a difference and x squared is a perfect square, 2 is not. So this is finished. It cannot be factored again. On number 3, they have a common factor of 25. So we would factor that out first. 225 is 25 times 9. So that would be 9x squared minus 1. That is a difference of two perfect squares, so it will factor again. The square root of 9x squared is 3x. One's a plus, one's a minus. 9x squared, 3x. Square root of 1 is 1. So that is complete because, again, this is not a difference of two squares. This is not a difference of two squares. So we must be finished. Finally, on number 4, this is a tricky one. Both of these numbers are even, so they're both divisible by 2. In addition, I can take an x cubed and a y to the 1st. That would leave me with 64x to the 6th, y to the 4th, minus 81, and the x to the 3rd is gone, the y is gone, so that's it. This is a difference of two perfect squares. So 2x to the 3rd y is going to stay in front, and this expression is going to factor. The square root of 64x to the 6th, y to the 4th would be 8x to the 3rd, y squared. So that is our first term in each set of parentheses. One is a plus, one is a minus. And the square root of 81 is 9. Notice the odd exponent. That means neither one of these can be a difference of two perfect squares. So we must be done factoring. Okay, final topic for this particular video is factoring trinomials, ax squared plus bx plus c, when our lead coefficient a is 1, which basically means we're looking at trinomials in this format, where there's no number in front of x squared. So x squared plus bx plus c. The key skill here is being able to find a pair of numbers that multiply to c, and that pen is not really behaving, add to b, whatever those numbers are. So let's look at a couple of examples here. On this first example, we have a c value of 20, and a b value of 9. So we're looking for a pair of factors that multiplies to 20 and adds to 9. That's what we're looking for. So when we look at factor pairs of 20, we could have 1 and 20. They could also be negative 1 and negative 20. 2 and 10, negative 2 and negative 10. Or 4 and 5, negative 4 and negative 5. Now keep in mind that this is an Algebra 1 skill, so if you know how to do this, great. You don't need to draw this chart. We would add those pairs of numbers together. And we're looking for positive 9, which is right here. That tells us that 4 and 5 are the ones we're looking for because they're the ones that add to 9. That's the number we're looking for. So our trinomial will factor into two binomials. Both of those binomials will always, for this type of factoring, start with x. What goes in the spots, as well as the signs, are determined by what we circled. We circled positive 4 and positive 5, so our factors would be x plus 4 and x plus 5. Let's do another one. Here we're looking for numbers that multiply to positive 12 and add to negative 8. Now that should tell us that in order for two numbers to multiply to equal a positive number and add to a negative number, they both have to be negative. But we'll go ahead and write out the entire list just to drive that point home. Factors of 12, positive 12, could either be 1 and 12, negative 1, negative 12, 2 and 6, negative 2, negative 6, or 3 and 4, which also could be negative 3, negative 4. We are looking for a sum of negative 8. So when we go in here and we start adding these up, you'll notice that negative 8 is right here, which means the numbers we want are the ones that add to negative 8, negative 2, negative 6. So this will factor into x minus 2 and x minus 6. Okay, time for more practice here. So again, we're looking for numbers that multiply this time to negative 15 and add to positive 2. So we need numbers that multiply to negative 15. That would be 1 and negative 15, or negative 1 and positive 15. Notice the signs are different because we need to multiply to a negative number. 3 and negative 5, or negative 3 and positive 5. Those are the only four options. So we go in and we add those up. They would add up to negative 14, 14, negative 2, and the one we're looking for, which is 2. So the numbers we want are negative 3 and positive 5, which means this factors into x minus 3 and x plus 5. Factors of negative 18 that add up to negative 7. So we have negative 1, positive 18, 1 and negative 18, negative 2 and 9, 2 and negative 9, could be 3 and 6, 1 positive, 1 negative. Those are all of your factor pairs for negative 18. Add those up. There it is. That's the one we want. We'll go ahead and finish it out because it's an example. So we want 2 and negative 9, x plus 2, x minus 9. We're going to try to cut back on the work on the next page and just start thinking it through. So again, here's a whole bunch more trinomials we're going to try to factor here. So we are looking for numbers that multiply to 24 and add to 14. Hopefully, you can come up with 2 and 12. So this would factor into x plus 2 and x plus 12. On the next problem, we're looking for numbers that multiply to 54 and add to negative 15. Again, this should mean that they are both negative. Given enough time, we should be able to come up with negative 9 and negative 6, which are the numbers that add up to negative 15. So we would have x minus 9, x minus 6. Numbers that multiply to negative 21 and add to 4. That would be 7 and negative 3. So n plus 7 and n minus 3. Again, these are the ones in class that we did on our own and then we got skill checked on. So we shouldn't really need this many examples of teacher prepared. But if you're really struggling, then we can talk through them. Multiply to negative 30, add to negative 7. That would be negative 10, positive 3. So this factors into y minus 10, y plus 3. Numbers that multiply to negative 48 and add to 8. It's kind of a tough one, isn't it? What do you got for me? It's not 1 and 48. It's not 2 and 24. It's not 3 and 16. It'd be 4 and 12. Positive 12, negative 4. That is what adds up to positive 8. So that would be, and that circle didn't really work out, so let's fix that. Positive 12 and negative 4. So a plus 12 and a minus 4. Okay, numbers that multiply to negative 72 and add to what? Well, there's no number there. Yes, there is. There's a 1 there. So they need to add up to negative 1. That would be negative 9 and positive 8. So x minus 9 and x plus 8. So that's something that can come up. If there's no number, remember there's always a 1. Finally, on letter G, you'll notice these are not written in descending order. So the first thing we should do is rewrite this expression so that the h squared term comes first, the h squared comes second, and the number comes last. That means we're looking for a pair of numbers that multiplies to 44 and adds to 15. Hopefully everybody can quickly come up with 11 and 4. So that would factor into h plus 11 and h plus 4. Same thing on letter H, x squared minus 10x minus 24. We're looking for numbers that multiply to negative 24 and add to negative 10. That would be negative 6 and negative 4. So that would be x minus 6 and x minus 4. Okay, final skill for this video. I know I said it was factoring, but in reality it's solving problems using that kind of factoring. So again, now we're going to transition from factoring problems into solving problems. And the only difference there is that after we factor, we then have to apply the zero product property. So again, it is very important that before we start, one side of the equation has to equal 0. That is already the case for our first two examples, so we shouldn't have too much of a problem there. What we're going to do is factor this into two binomial factors using what we just talked about. We're looking for two numbers that multiply to 12 and add to negative 7. That would be negative 3 and negative 4. Those are the ones that add to negative 7. So that'd be x minus 3, x minus 4 equals 0. Now we're going to apply the zero product property, which says that either x minus 3 has to equal 0, or, just like we did before, x minus 4 has to equal 0. Each of these is a one-step equation. So the first one, we would add 3 to each side. The second one, we would add 4 to each side, just like we did before, giving us two answers, x equals 3 or x equals 4. On letter J, we're looking for a pair of numbers that multiplies to 9 and adds to 10. That would be 1 and 9. So we'd have c plus 1, c plus 9 equals 0. Then we break it up. C plus 1 equals 0, or C plus 9 equals 0. Again, each of those is going to get solved. Now once you get good at this, you don't have to show nearly this much work to get to the answers. But until you know what you're doing, you should show your work every time to avoid silly mistakes. So our solutions for letter J should be C equals -1 or C equals -9. Now we get to M and N. What's the problem? It's the same thing we discussed up above. These do not start off equaling 0. So your first step has to be to move that number to the left side so that you can write it as an expression equal to 0. Now keep in mind, it is possible that there could be like terms here to be combined, but there's not on either one of these examples. So then we're going to factor. We're looking for numbers that multiply to -15 and add to -2. That would be -5 and +3. So that's x minus 5 and x plus 3. And we're going to split that up into two separate equations using the zero product property. And then we're going to solve. So plus 5 on each side for the first equation gives us x equals 5 for our first solution. X plus 3, we would subtract 3 from each side, which would give us x equals -3 for our second solution. Finally, for letter N here, we're going to add x to each side. Again, it doesn't combine with anything, so it's just going to turn into a trinomial, x squared plus x minus 20 equals 0. And that's what we need in order to factor, is we need it equal to 0. We're going to factor that by looking for a pair of numbers that multiplies to -20 and adds to 1, because there's an invisible 1 there. That would be +5 and -4. Those would be the numbers that add up to +1 and multiply to -20. So x plus 5 and x minus 4 are my factors. X plus 5 equals 0, or x minus 4 equals 0, allows me to find my solutions with the zero product property. So then I would subtract 5 from each side of the first equation, giving me the solution x equals -5. And I would add 4 to each side of the second equation, which would give me x equals 4. So my solutions are x equals -5 or x equals 4. Fairly certain that that is the last slide that I haven't already put on video. I have to wait on the computer to decide to change the page, and it is. Again, this other part of this lesson, factoring by grouping, can be found on a separate video. So that completes this part of the lesson. I hope that you're preparing for your finals.